Okay, we're back again with our third video about solubility equilibria. And this is the common ion effect. And what happens to the solubility when you have another compound that has an ion that's the same as the ion in your original compound. So our original compound here is, um, lead 2 iodide. And we're just going to find, first of all, straight off, molar solubility of lead 2 iodide in water. Same kind of calculations we've done before, and just straightforward. I have a KSP of lead iodide, and here's my ion product expression with the lead and the iodide. And to find the molar solubility, I'm looking out for, remember, molar solubility is X relating to the lead iodide. Which ion would give me the molar solubility? That's in the 1-to-1 ratio. The one that would be the lead ion. So I want to find the concentration of the lead ion. Setting out my ice table, the lead dissociates to an X amount, the iodide into the 2X amount, and if I write my KSP expression, KSP is equal to concentration of the lead, of course, times I minus squared. So all of this X is the lead, 2X is the I minus what goes in here. So I get X times 2x squared. That's equal to 4x cubed. And I have my KSP number, 7.9 times 10 to the minus 9. And if I solve for x, I get 1.3 times 10 to the minus 3 per liter. So that's the molar solubility of lead 2 iodide, just in water. Well, suppose we had a solution of sodium iodide. Suppose we had some extra iodide ion, and we put that in there. So I have extra. So I have now increased our iodide concentration. So this has now gone up. What happens to the equilibrium? Well, whatever disturbance you make to the equilibrium will try to react against it. So if the product side increases, then the equilibrium shifts over to the reactant side. And so what would you observe? You would observe more solid being formed, because on the reactant side, the reactant is lead iodide solid. So we're just looking back at equilibrium with Chatelet's principle, how that changes. So as I add more I minus, I have the shift over the opposite side of the equilibrium to the solid side. So it increases kind of at C for that I to precipitate. How can we calculate this change in the solubility? That basically it means I will have changes in the molar solubility. If I'm getting more precipitate, what does that mean? If I'm getting more precipitate, it means that, well, let's find out. Let's look at the calculations. So I'm going to put the lead 2 iodide in a solution of 0.1 molar sodium iodide. Okay, and so initially I don't have any lead dissociating, but I already have 0.1 molar iodide solution, and that is already there. So that we're not going to multiply it by 2. This coefficient always relates to the change rho. The initial concentration comes from the NaI, not from PbI2. So like my ice table before, I have X is the increase in lead, and 2x is the increase in the iodide. And here's my equilibrium expression. So this goes into the lead, this is for the iodide, all in it and squared already. Now, of course, this will become a terrible quadratic equation if we try to solve it just like that. So we want to use our simplification with how big the KSP is versus my initial concentration, which is 1 molar. Even if I multiply this by 1,000, this 1 molar is still larger. So that allows me to ignore this small change in the iodide concentration. So I can ignore it, and essentially becomes a much simpler calculation to find X. To find X now in sodium iodide, this is the molar solubility of lead 2 iodide, which is different. Let's see how different, what happened. So what happened? Compare in pure water, molar solubility was 1.3 times 10 to the minus 3. And now in NaI, look how much smaller this is. So as in a common ion, in a solution with a common ion, then the solubility decreases because that shift in equilibrium. So we have a decrease in the molar solubility with a common ion. And one really interesting thing to think about this way is something that's really pretty insoluble. Kidney stones, oh, very painful situation if anyone's ever gone through it. I haven't personally, but I can imagine how painful that is. So kidney stones are compounds or precipitates of calcium oxalate or calcium phosphate or magnesium ammonium phosphate or a mixture of all three. So we're just going to concentrate on the two calcium ones. And so in the kidneys, when you have the urine becomes too concentrated, you'll have a higher percentage of those ions and they can precipitate. And this is where they go down the ureter, down into this passageway, which I'm sure is very painful. So those people who are prone to kidney stones, I think, have to watch their diet in calcium foods and oxalate foods and phosphate foods, and I think that's probably not that much fun. So let's just determine how much oxalate is needed. Suppose the calcium in the urine is already present, and we're doing a concentration. And unfortunately, the concentration is in grams per liter, but that won't stop us because we can still find a concentration in moles per liter. So just give us some room here. We're looking for the oxalate concentration. It's not a problem, but I want to just go back and reiterate what our process is. And the process first is to concentrate on the salt that we're looking for, is calcium oxalate. And so on the ion product expression or dissociation expression, we get calcium and oxalate. And so our KSP, of course, is the concentration of calcium and the oxalate. Right? And so we're looking for this concentration of the oxalate here. Our ice table, so I, C, E. So the initial concentration is there already, but it's in grams per mil for the calcium. And we need to change it to moles per liter. And that's pretty straightforward. 1 mole, this is 40, 1 or something. And we'll just do that calculation, find out the concentration. And this is 0.133 moles per liter. So that is our initial concentration for the calcium. We don't have any oxalate. Imagine that the urine is there already with calcium ions, but we haven't introduced the oxalate ion. So we're looking for that. So that's 0 initially. And as always, this is going to produce some ions here. We have 0.133 plus that small change, and of course that change for the oxalate. We're going to put these into our KSP expression to find out what our molar solubility is. So we'll have KSP. We get to the concentration of calcium plus 2 for the oxalate. Of course, this is all the calcium. This is the oxalate. And so we have 0.133 plus X. And we have, this is X. Now, Of course, this might give us a quadratic because I have x times x and everything. This KSP number is 3.3 times 10 to the minus 9. So we're going to approximate it. This 0.133 is still much bigger than our KSP, which is 2.3 times 10 to the minus 9. So remember, we can make that simplification. We can move that x, and then this becomes a much easier calculation. And it's pretty straightforward to find x now. So what is the oxalate concentration? Remember, we're looking for this oxalate concentration. X then becomes equal to, this becomes equal to 1.7 times 10 to the minus 8 molarity for the oxalate concentration, which is really low. So that's a pretty high calcium concentration. So if any oxalate is present, then it's probably going to precipitate pretty fast. But unfortunately for those people who have to stay away from things like chocolate, that's pretty sad. Well, of course, we mentioned that calcium oxalate isn't the only ion in solution or compound that can make kidney stones. We have calcium phosphate too. If we went through the same process, we would find